Have you ever stopped to think about the sheer magic packed into modern medical devices? I mean, how a tiny machine can understand the chemistry of your body almost instantly? Well, today, we're going to pull back the curtain on that invisible science. We're talking about the tech that powers everything from those huge, complex lab analyzers down to the sensor you might have in your own home. Let's get into it.
Seriously, just think about this for a second. Someone with diabetes uses a glucose monitor. They take a tiny pinprick of blood, touch it to a little plastic strip, and boom, in moments, a number appears that could literally save their life. How does that even work? How does that little box translate a chemical fact, the amount of sugar in your blood, into an electrical signal, into a number you can actually read? That's the exact mystery we're going to unravel right now. So here's our game plan for today. We're going to start with the familiar stuff, the devices you've probably seen. Then we'll dive into the fundamental science and explore the four main languages these sensors use to eavesdrop on your body's chemistry. We're going to take a really deep look at two of the most important methods, potentiometry and amperometry, before we zoom back out to see how all this incredible science is changing our lives. So what devices are we actually talking about here? Well, it's a whole family of them. You've got the pH meter in a science lab checking how acidic something is. You've got coagulation monitors that measure blood clotting before big surgery. And of course, there's the personal glucose monitor. They might look totally different, but believe it or not, they all share the same secret ancestor, the science of electrochemical detection. Okay, so how do these things actually listen to a biological sample? Well, scientists have figured out four basic ways to turn a chemical event into an electrical signal that we can measure. You can really think of these as the four fundamental languages of biosensing. And here they are, the big four. You've got potentiometry, amperometry, coulombrometry, and resistance or impedance sensing. Each one measures a totally different electrical property, which gives scientists this amazing, versatile toolkit to build a sensor for pretty much anything. We're really going to focus in on the first two, because they're at the heart of so many of the devices we've been talking about. First up, potentiometry. The key thing to remember here is that we are measuring potential, which is just another word for voltage. And crucially, this all happens when there's no electrical current flowing. It's kind of like measuring the pressure difference between 2 points in a water pipe before you open the valve and let any water flow through. Next up, we've got amperometry. And this is kind of the flip side of the coin. Here, we don't just sit back and measure potential. Nope, we actively apply a voltage to force a chemical reaction to happen. And then we measure the flow of electrons that comes out of that reaction. That flow, that's the current. This method is all about counting how fast those electrons are moving. And just so we cover all our bases, there's also coulometry. Now, if amperometry is like measuring the flow rate of a river in gallons per minute, coulometry is like measuring the total number of gallons that have flowed past it an hour. It adds up the total charge from a reaction. This is super important for things where you need to know the total amount, like figuring out the exact thickness of a metal coating. And finally, resistance or impedance sensing. This method is pretty straightforward. It just measures how much a sample fights against the flow of electricity. When something biological happens, like a single blood cell squeezing through a tiny opening, it actually changes that resistance, and the sensor picks up on that tiny change. It's actually the core principle behind most modern automated blood cell counters. All right, let's really dig in. Time for our first deep dive into potentiometry. Remember, this is the one where we measure voltage, but with no current. It's the science that makes things like a simple pH meter work. Now, this is where it gets really clever. See, you can't just measure the potential of one thing by itself. You need something to compare it to. So potentiometry always uses two electrodes. First, you have the indicator electrode. Let's call it the measurer. It's built with a special surface that's super picky. It only reacts to specific ions. That interaction is what makes its voltage change depending on what's in the sample. But a changing measurement is totally useless without a fixed starting point. And that's the job of the reference electrode, our ruler. It's designed to have a rock-solid, unchanging potential. It's the constant baseline we need. The device then just measures the voltage difference between the two. Simple as that. So how do we make that super stable ruler? Well, this table is the secret. Ages ago, scientists agreed on a universal baseline. They called it the normal hydrogen electrode, or NHE, and just defined its potential as 0. It's like agreeing on what 0 degrees Celsius means for temperature. Then everything else is just measured against that. So as you can see, a saturated calomel electrode will always read 0.241 volts compared to that baseline. A silver/silver chloride one always reads 0.198.
By having these universally agreed upon values, we can build a reliable ruler for pretty much any measurement we want to make. And of all the options out there, why is the silver/silver chloride electrode so incredibly popular? I mean, you see it everywhere. This quote from the source material says it all. It just ticks every box for commercial production. It's cheap to make, it's small, it's tough, and you can churn them out by the millions. It's that perfect sweet spot where good enough science meets practical real-world engineering. But, and this is a huge but for engineers, there's a catch. That stable silver/silver chloride electrode, it's not perfectly stable. Its voltage actually wiggles a little bit depending on how many chloride ions are in the sample. This is a classic engineering trade-off. For a super high-precision experiment in a lab, that's a big problem. But for a disposable sensor that needs to cost pennies, it's a known variable. You can control for it and just factor it into the device's final calculation. Okay, now for our second deep dive. Let's circle all the way back to where we started, that mysterious blood glucose monitor. This thing is an absolute masterpiece of amperometry. It's not just passively reading a voltage. No, it's actively driving a chemical reaction, and then it counts the electrons that come flying out. Okay, so let's walk through this step by step. First, you put that drop of blood on the strip, and a chemical reaction kicks off. The whole key here is that this reaction creates iron ions, Fe2+, and the amount of this stuff it makes is directly proportional to the amount of glucose in your blood. More glucose means more Fe2+. Simple. Second, the meter applies a very specific voltage, a bias potential, to the strip. That voltage is tuned just right to trigger another reaction. And third, that applied voltage forces those Fe2+ ions to give up an electron, turning them into Fe3+ ions. That movement of electrons is an electrical current. The meter measures that current. And since the amount of Fe2+ was tied to the glucose, that final current reading tells you your blood sugar level. It's just brilliant. And this isn't just a guess. It is incredibly precise. The standard potential you need for that specific iron reaction is exactly 770 millivolts when you measure it against that universal NHE baseline we talked about. The engineers who design these sensors have to know that number and apply exactly the right voltage to make the whole thing work every single time. It's a beautiful example of how precise the underlying chemistry has to be. So, in a perfect world in a lab, how do scientists get the absolute best measurement? They use this, the 3-electrode system. You've got your working electrode, that's where our ion reaction is happening. You've still got the reference electrode, our stable ruler, but here's the game-changing addition, the auxiliary electrode. The actual current, the flow of all those electrons, happens between the working and the auxiliary electrodes. This setup is so clever because it completely shields the reference electrode from that current. It protects its stability. This lets you drive a really strong reaction without messing up your ruler, which guarantees the highest possible accuracy. This is really the story of lab science meeting real-world engineering. That 3-electrode system is the gold standard in a lab, but it's way too complex and expensive for a disposable strip you're going to use once and throw away. So for these consumer diagnostics, engineers came up with a brilliant compromise. They combined the reference and auxiliary functions into a single sacrificial electrode. It acts as both the stable reference point and the path for the current. Now, is it as perfectly precise as the 3-electrode setup? No, but it is more than good enough for its purpose, and it's what makes these life-saving devices cheap enough for everyone. And that brings us full circle. We've gone way down into the weeds of the science of potential and current, but the real magic is seeing how all this knowledge has been shrunk down from a massive lab bench into a tiny device you can hold in the palm of your hand. The applications in modern medicine are just everywhere. These principles are used to measure critical electrolytes in your blood, things like potassium, sodium, and calcium. They're the absolute workhorses inside those giant automated chemistry analyzers you see in hospitals. You know, the ones running hundreds of samples an hour. And of course, the technology has been miniaturized and microfabricated to create the portable, personal devices we started this whole journey with. And to put a real name on it, the source material points to the Abbott Architect system. This is a real-world, widely used clinical analyzer that runs on these exact same potentiometric and amperometric principles, delivering fast, accurate results for doctors and patients around the world every single day. And the impact goes way beyond just the doctor's office. This same core technology is being used for environmental testing, checking for pollutants in our water. It's used in food safety to find contaminants. And of course, it's still a fundamental tool in scientific research, constantly pushing the boundaries of what we can measure and what we can understand about our world. So there you have it. We've seen how a few basic principles of physics and chemistry can be engineered into these amazing devices that literally read the language of our bodies. From a simple voltage difference to a carefully controlled flow of electrons, these sensors turn the invisible into information. It really makes you wonder, as this technology gets even smaller, even faster, and even more sophisticated, what secrets of our biology will they help us unlock next? Thanks for tuning in.